I wanted to talk to you about the elliptic curve digital signature algorithm, ECDSA, and elliptic key public key cryptography. We very briefly covered this once before, but it was kind of at a high level, and I want to actually get into it with some examples and some real numbers and talk about what the functions are and what they do. So, an elliptic curve. Basically, the curve I've got over here is an elliptic curve, and it corresponds to these equations. Y squared equals x cubed plus a times x plus b. And the curve that I'm using for the examples is got for a and b minus 3 and plus 4 for the constants. That's a relatively good one to work with in a teeny curve like this. Teeny, I mean, because I've got from 0 to 3 or 0 to 4 in one direction and 0 to 4 in the other direction. So this is really teeny. But it illustrates all the things we need to know about this curve. And I'm going to use this and some other examples. Now, this is a good curve where it looks like this kind of funny U-shaped on its side thing. We can look at bad curves, and let me bring in an example of other curves that you can get with elliptic curves. And first of all, there is the entire set of curves that are not good curves. And I've kind of color-coded this, but let me actually get it up here so you can look at it. The color coding is the good curves are in green and the bad curves I have stuck in red. And it's not very hard to figure out which one it is are bad curves. And make it so you can see it. If you've got a curve that has multiple solutions on the axis, it turns out to have all sorts of problems for doing this computation. You see these used as examples in some stuff in some of the on-the-web explanations of elliptic curves, but they cause problems. If it doesn't have the little bulgy thing out here, it's just like, yeah, it'll work, but not well. So all of these are bad curves. And, if you just look at the slope of the top half of the line so you can work with it as a function, it's real easy to figure out that what you really want is some curve that has a slope that switches direction up here and comes down. And these are easy to identify which ones they are. These ones that don't quite switch direction, okay, which is all of those that I'm pointing at, they're just not so good, okay? And if you have multiple solutions where it crosses the x-axis, that's these with the little circly whoopy thing, those things aren't good either. So picking out a decent curve has that kind of a criteria. You want one that has that kind of switch direction. It all works out better in the mathematics. And consequently, the curves that are already picked out by people for use all have this kind of a property. Now, there are, other things that you will find about elliptic curves. For instance, if you start doing the research, you'll find the elliptic curve, what do you want to call it? Things like Sony's encryption was broken as being bad for the elliptic curve. This XKCD comic summarizes their problem. There is a K value that you're supposed to use as a random value. And this XKCD has their choice for the K value. I mean, they didn't return 4, but it was supposed to be a random number. And if you return a constant, then people can use multiple iterations of your curve and factor it. And that's how they goofed it up. If you don't do it right, yeah, it'll be broken and it'll be wrong. And it's relatively complex. Now, there are a bunch of curves out there that are already pre-built. Okay, and I'm going to talk a little bit about the pre-built curves. This is from a graduate course on elliptic curves. And the first one is P256. It's also referred as spec 256R1. If you go looking in the Ethereum source code, you'll see it referred to as spec 256R1. But if you look in like Go language, it just says P256. And the National Institutes of Standards, this is the curve that they picked. It's got decent properties with the caveat that maybe they picked a curve that has something wrong with it because they were inserting backdoors into some code. And this one is required for things like TLS 1.3, the current version of TLS that everything in the world runs on. This is the only required elliptic curve. Now, realistically, although this is required in the standard, that doesn't mean it's required for you to use. There is this other curve, okay, curve 25519, and curve 25519 is the one that people like Facebook, Google, Instagram, all of those guys are using. And the guy who invented elliptic curve cryptography, okay, he's the one that came up with curve 25519. So it wasn't developed by the government, and we're pretty darn certain that that is a good curve to use. So, and it's also available in pretty much every library I have seen everywhere. So you don't have to use this other curve unless, you're trying to meet government standards on a DoD contract and you have to use it. But the rest of the time you can pick a different curve. Certainly this is the curve that I use all the time for encryption when I'm working with elliptic curves. So the difference between these curves, okay, is one of them's going to look like this and the other one's going to look like that. As in terms of reliability and what it does, as long as both the sender and the receiver in the encryption use the same curve, everything is okay. Now, this means that when they use the same curve, there are certain values. The G value that's going to show up in this data and other things that they're both going to know on the sending and receiving end. The algorithm is exactly the same either way. What curve you use determines how the points get mapped, and you have to agree on one curve, but you don't have to use, you don't have to have a deep understanding of what the curve is or what it does. You just pick one and you go with it, and both sides have to agree on it. Okay, so we have an elliptic curve, and its graph looks something like this. Now, one of the properties that you're going to see is this is a continuous graph of the curve. Later, we're going to get into discrete graphs, where it's just points on integers. It works the same way. But it's easier to show things, at least to start off with a continuous curve. So I've got a teeny curve here that we're going to work with. And the first thing we're going to talk about is addition.